Before we tackle the topic that is uniform flow, let us first define what flow is. Flow is the action or fact of moving in a steady continuous stream, whereas the uniform flow is a flow that is rare. But if it were to occur in a channel, the depth and velocity will not vary along its length, or in other words, terminal conditions would have been reached. Now, let's go to the topic 10.3.1, that is channel geometry. In this chapter, we consider mostly regular channel shapes. Three common geometric figures are shown in figure 10.4. The first is the rectangular section. It is the simplest channel shape. The cross-section is given by the formula A equals B times Y, wherein B is the width of the channel bottom and Y is the vertical height of the wetted perimeter. The wetted perimeter, or P, is the length of the line of contact between the liquid and the channel. For a rectangular channel, it is given by the equation P equals B plus 2Y. The hydraulic radius, or R, is the area divided by the wetted perimeter, and in the case of the rectangular section, it is equals to By over B plus 2Y. We will go now to the trapezoidal section. Its area is defined by A equals By plus 1/2 y squared multiplied by m1 plus m2, where m1 is the ratio of the horizontal to vertical change of the wall on one side and m2 is the corresponding quantity on the other wall. Its wetted perimeter, or P, is given by the equation P equals B plus Y multiplied by the square root of 1 plus m1 squared plus square root of 1 plus m2 squared. The free surface width B for the trapezoidal section is given by the equation B equals small b plus y multiplied by m1 plus m2. Let us go now to the circular section. This section is one of the most commonly used in the free surface flows, such as in drainage and in sewer systems. Its area is given by the equation A equals d squared over 4 multiplied by alpha minus sine alpha multiplied by cosine alpha, wherein alpha is equals to the arc cos multiplied by 1 minus 2 multiplied by y over d. Its wetted perimeter is given by the equation P equals alpha multiplied by d. Its free surface width is given by the equation B equals d multiplied by sine alpha.
So let us proceed to the next topic, which is the equation for uniform flow. When does uniform flow occur? It occurs when the depth and velocity do not vary along its length, given that the terminal conditions are reached or applied. These are the things that affect the uniform flow: energy grade line, water surface, and channel bottom. So this guy right here is Antoine de Chauzy. His work made a great impact in the world of fluid machineries, but before that, he was a French hydraulic engineer and author of a basic formula for calculating velocity of a fluid stream. Given the formula of V is equals to C square root of R S sub 0, where V as the velocity, C as the Chauzy coefficient, R as the Reynolds number since the flow is considered completely turbulent, and S sub 0 is the slope of the channel bottom. Robert Manning continued the works of Antoine and made some improvements and made it more accurate, given the formula of C is equals to C sub 1 over N times A multiplied by R raised to 2/3 times square root of S sub 0, where C sub 1 is 1 for SI units, S sub 0 is the slope of the channel bottom, R for the hydraulic radius, N for the Manning coefficient, and C for Chauzy coefficient. Combining the equation stated before, we have Q is equals to C sub 1 over N multiplied by A times R raised to 2/3 times square root of S sub 0, where Q as the flow rate, and so on and so forth. So here's the table for Manning coefficient N.
Most efficient section. Specification to attain appropriate geometrical cross-section provided that flow, Manning coefficient, and slope are known for designing a channel that conveys uniform flow is one of the main thought of this subtopic. Once chosen, An optimum sizing of the cross-section can be based on the criteria of minimum resistance to flow. The flow resistance per unit length equals wall shear stress times wetted perimeter. Using a control volume for uniform flow, we get this equation. Furthermore, we have to satisfy the Chassis-Manning equation, since flow, Manning coefficient, and slope are given and hydraulic radius equals area over wetted perimeter. The Chassis-Manning equation is given in this formula. As an example, consider a rectangular channel with width b and depth y. The best hydraulic cross-section is obtained by rewriting the previous equation such that area becomes a function of b only. Therefore, we express p in terms of a and b, using a equals b times y and p equals b plus 2y. Substituting this equation into the equation p equals c multiplied by a raised to the power 5 halves yields this equation. And by setting the derivative of a with respect to b into 0, since the objective is to find the value of b that minimizes area. The result is this. Thus, if the width of the rectangular channel is twice the depth of the flowing water, the water will flow most efficiently. The optimum criterion based on the flow resistance cannot always be used, and in fact may be less significant than the other design factors. Additional aspects to be considered are the type of excavation, and if the channel is unlined, the slope, stability of the side walls, and the possibility of erosion of the bed.